right, so we're gonna start video number 6 here, and we're going to be learning about Hess's law. And here's the idea behind Hess's law. Most reactions actually take place in multiple steps. So whenever we have an overall energy for a reaction, which takes place in a multiple step, or in multiple steps, we can actually add up all the individual enthalpy changes for each step, and that'll give us the overall enthalpy in the problem. Now, if you take a look in your notes, we say that enthalpy is a state function, and all that means is that to get from point A to point B, it doesn't matter how you get there. So if I wanted to go from here to here, let's say these are my reactants right here, and these are my products. If I go there in one step, or if I go there in 3 little hippity-hoppity steps, the overall change in enthalpy from here to here, that's the amount of energy that we've gained or lost, will be the same. So what often happens is you can have some steps in a reaction that are exothermic and others that are endothermic in a multi-step reaction that takes you from reactants to products. And here's a good example of this here. If we were to start off with N2 and 2 O2s, and we made that go to O2 and 2NO. So if we start down here, right, and we wanted the reaction to go from these two reactants to these 2 products, it would actually cause, we'd actually gain 180 kilojoules of energy. But then if we took those 2 things, O2 and the 2NO, and we reacted them together and we formed 2NO2, that reaction would actually lose 112 kilojoules of energy. But if you add those 2 together, the net result is the reaction gained, these 2 reactions together gained 68 kilojoules. That would be the same thing. And what's kind of cool about this, I don't know if you've probably not seen this before, but what you can do is whenever you have multiple steps in a reaction, you can actually add them together, and you kind of do like a mathy thing where you can cancel out things that are similar. So if you took a look right here, do you see how we could go like this and go, okay, if I were to cancel out this O2 and this O2, right, and these 2 NOs and these 2 NOs, do you see how that would give us N2 plus 2O2, and that would give us 2NO2. And if you take a look here, this little part of the graph right here shows what would happen if we just did this in one step. And you notice how the energy is the same in both cases. So what Hess's law essentially says is that it doesn't matter if a reaction takes place in multiple steps or one single step, the amount of energy change between the reactants and products will always be the same. Now, what we're going to do is kind of weird. What we're going to do is we're going to be given a number of individual steps. Like if you take a look down below here, we're given 2 individual steps, and then we're going to be given an overall reaction, and we're going to have to, based on the individual steps, figure out how much enthalpy there is in the overall reaction. Now, here's some guidelines that will not make sense until we actually start doing this, so follow along with me. If we ever take a reaction and we reverse a reaction, the enthalpy will be reversed. And if we ever multiply the coefficients, these numbers in front, by any factor, we have to multiply the change in enthalpy by that number as well. Now, the last one where it says that change in enthalpy is in joules per mole, which means if you change the number of moles, you've got to change the change in H, will not really be used for us right now. But let's take a look at this right here, and we're going to call these maybe reaction step 1 and step 2. Now, if we take a look at this right now, what we want to do is we want to be able to add these 2 reactions up to end up with this reaction, because this is the overall reaction. Now, if we take a look at this here, the way I do this first is I look at it and go, all right, what do we have on this side? And let's take a look at the first one here. Do you see how we have a C right here and we have a C right here? So they both have a C, so that's actually pretty good. And we don't want to multiply this or anything, but that's the only place there's C. There's nowhere else is there a C right here. So we want to keep this reaction kind of as is. So we're going to keep this the same, and that means that the change in enthalpy for that one step is going to be equal to negative 393.5 kilojoules. Now let's look at the second step. Now remember, when we add these 2 steps together, we have to end up with this overall reaction. If you take a look here, do you see how the CO, the only place we have CO is on this side? It's not anywhere else. But do you see up here, we need to have CO on that side. So the only way we can make that happen is if we reverse this reaction. So if we reverse this reaction right here, I'm going to write it down below. I'm going to write it as this. So if you see that, this is exactly the reverse of this. And what that means is that we've just changed the enthalpy as well. The sign of this has to change as well. So that's going to be equal to plus 283.0 kilojoules. Yeah? Now, this no longer exists. Only these two exist, these two reactions. This becomes our new 2. Now, if we've done this correctly, our goal will be to, when we add up this step and this step, it'll equal this right here. So if we take a look, let's see what cancels out. Do you see how we have a CO2 right here and we have a CO2 right here? They cancel. Do you see how I have a half an O2 here and a full O2 right here? So this half O2 right here, wouldn't that give me 1/2 O2 down below here? There's only one carbon on this side. So if we treat it like an equation, we have a carbon here, we have an O2, and we have half an O2, that gives us half an O2. Then we have on the other side, we have a CO2, which we just canceled out, and we have a CO. So the only things that actually did not cancel out were this, this, and this, but actually only half of that, and that gives us this. So that means when we do our overall enthalpy for the reaction, we have to add these two together. I'm going to call it change in enthalpy for the reaction because it is for the reaction. It's going to give us minus 110.5 kilojoules. Now, that you may or may not feel that comfortable with this, but let's try another problem. And this problem is going to be a little more tricky, and I'll be really candid. When I did this on my own, it took me a little bit of going back and forth. It wasn't like I just sat down and went, oh, clearly this is how we solve this. I actually had to go back and forth to try and figure this out. So if you wanted to, you could number these if you'd like and go, all right, this is reaction 1, 2, and 3. And we're going to have to do different things because ultimately we want to end up with this right down below here. So I took a look at the equations and went, all right, what do I have to start off with here first? And when I looked at the first one here, I looked at this and see how there's 2 NOs right here, and that seems like there's 3 NOs right here. So, I mean, we want to have NOs in here, so that might be a good place to keep. But then I looked at the equation even farther, and I looked at number 3, because I'm trying to find something that's going to be really easy to work with. The only place that we have N2O, isn't it right here? Right? And that we need to have N2O on the end here. And so if we took this equation right here, we need, the only place we have N2O is here. We'd have to divide this by 2 to get to this, right? So if we were to divide this by 2, wouldn't my equation number 3 right here, if we wrote it out, wouldn't it now be N2O as a gas plus N2 plus 1/2 O2 as a gas? And incidentally, when we do this, since we divided the entirety of this by 2, we also have to divide the change in enthalpy. So the change in enthalpy for this right here is going to be negative 163.2 divided by 2. That's going to be our change in H for this step. So then we move on. We're like, all right, what do we do next? Well, I took a look at this and I went back and forth. And remember I told you how I know that we need to have 3 NOs, right? So if I took a look at this one right here and thought, well, what can we do with this? Well, we have 2 NOs on this side and 2 NOs on this side, right? The way it's written, these would just cancel each other out, and we need to have 3 NOs over here. So if I were to take this and flip it around, that would give us the number of NOs that we need on that side. Here's the problem. It would give us 4 NOs, and we only want to have 2. So what we're going to do is we're going to reverse this, and we're going to divide it by 2. Now, clearly, as I'm doing this right now, this is me, before I even did the video, me spending probably 5 to 10 minutes going back and forth and trying to figure out what things I should move around and whatever. I didn't just look at it and go, oh, clearly we have to reverse and divide by 2. Now, students overall tend to enjoy these because they're kind of like puzzles. So if you're like, try something like, oh, that didn't work out, that's all right. Keep on working on it. It will eventually fit. So what I was saying is that you may have to go back and forth to solve these. So I'm going to take this and I'm going to reverse it and I'm going to divide it by 2. And when I do that, I end up with this. I'm going to take the NO2 and it's just going to become a regular old NO2. And it's going to become an NO on this side. And it's going to become 1/2 O2. This is the new flavor number 2. And in this case here, I flipped the reaction, so the sign on this is going to have to change. So it's going to become plus 113.1 kilojoules, and I divided it by 2. So that's my new change in H right here. And my third one, because we have the NO in the correct spot right here, we're going to leave it exactly as it is. So we're going to go N2 plus O2 and we're going to form 2NO. The new change in H, the same change in H is going to sit plus 180.7 kilojoules. Now, I want to verify that we've done this correctly, because if we do this correctly, what we need to be able to do is we need to add up everything on the reactant side, everything on the product side, and canceling out units, and we need to end up with this. So if I start over here and try and cancel out units that need to be canceled out, I end up with this. Oh, by the way, I did not put an arrow here. That should be an arrow. I was a little bit confused. This N2 cancels with this N2. This O2 right here cancels with this half O2 and this half O2. This NO and these two NOs give us 3NO. And this N2O and this NO2 are the only other things that are left. And if you compare these two, and again, you have to keep the states of matter in, because in this case, it doesn't really matter, but you may get sneaky problems where if you have a liquid NO2 and a gas liquid N2O and a gas N2O, they do not cancel each other out. This works. That means all we have to do is add up all three of these. And when we do, the change in enthalpy for the reaction, the entire reaction, is equal to 155.65 kilojoules. Now, this is in a world that ignores significant figures, and we know that we can't ignore significant figures, can we? So we're allowed to have 4 significant figures because each of these has 4. We're going to draw our line of death right here, and it's going to become 155.7 kilojoules. Now, we will definitely be practicing some of these, because you will not get good at them just by looking at this video. You have to practice them. Hopefully this has been helpful, and we will do some of these next time we meet. Take care. Bye.